My name is Sagar Gupta,
And I'm Sumanth Ratna.
and this is our project on protein secondary structure assignment by clustering amino acid residues in the space of topological descriptors.
As you may know, protein structure and function are very closely related. By studying protein secondary structure, which describes the chemical interactions between amino acid residues, we can gain a better understanding of protein structure-function relationship. One problem with the current approach to SSA is that different algorithms often provide different results. This mainly has to do with the input data they consume and the parameters they use.
In order to solve these problems and attempt to create a novel and objective method of secondary structure assignment, one of our mentors, Mr. Combs, used the Delaunay tessellation of proteins to represent their structure in the form of 64 topological features. He then used this data to train a random forest classifier to attempt to create a predictive model of secondary structure. However, the issue with this is that random forests are a supervised method of classification, meaning they require pre-labeled data to train and learn on. To eliminate the need for already labeled data, we focused on using an unsupervised clustering model, in this case k-means, to cluster the same topological data and look for new definitions of protein secondary structure, as well as the specific features that contribute most to secondary structure elements.
After collecting our data, we applied dimensionality reduction to visualize our data and determine which features contributed the most to the dimensionality reduction. We then used scikit-learn to run k-means clustering with 3 clusters. After running a UMAP 2D projection of the k-means clustering data against the DSSP labeled data, we were able to map cluster 0 to helices, cluster 1 to strands, and cluster 2 to coils. We achieved an 83% overall agreement with DSSP labels. Our confusion matrix shown here shows that most of the misclassified residues were coils. This is expected due to coils not having as defined of a structure as either helices or strands.
Next, in order to determine the most important features in our entire dataset, we used principal component analysis to reduce and plot all of our data in 3 dimensions. We were able to identify 5 key features, 49, 13, 4, 5, and 1, as the most important features in our dataset. In addition, we plotted the distribution of the means for each feature across all 3 clusters and found the same 5 features in the PCA to have the highest variance. Since these results agreed with the PCA, the clustering algorithm was successfully able to capture the most important features of our dataset. For further analysis as to why these features were deemed important, we chose the first feature of the 5 important ones and plotted this distribution of values. Feature 1 maps to coordinates 0, 0, 0, and thus represents the frequency of simplices with sequentially adjacent residues in a manifold. We can see that there are distinct thresholds that allow us to determine which cluster a residue belongs to based on its value for feature 1. Looking at the reference image for the structure of a helix, this cutoff at value 2 makes sense because a higher number of more close together residues are likely to form a helix.
This bar plot shows that different clusters have significantly different fine psi angles. The fine psi angles both describe an amino acid's peptide bond. Both angles have a range from -180 to +180 degrees inclusive. This plot shows the histograms for the phi angles of the 3 clusters. Although the 3 histograms generally overlap, we see that most of the positive phi angles were coils. This suggests that we may be able to use phi angles as an input for SSA. Here we can see that once again, most of the helices lie in a small range. Due to the high overlap of the psi histograms, the phi angle may be more useful in SSA. Here we can see that the average phi angle for strands was much smaller than that for helices and coils. And here we can see that the differences between the angles are much more distinct for psi than for phi. We also ran 3 statistical tests with the same purpose, to see if the mean phi angle was different across all 3 clusters. As you can see, our results were statistically significant with a p-value of approximately 0. Our results were also statistically significant for the mean psi angles.
Since our model achieved an 83% overall accuracy, we know that a topological representation successfully captures protein structural elements. We also found statistically significant differences in the phi and psi angles among the clusters, and we were able to pinpoint key features that allowed us to determine what types of features were most valuable in secondary structure assignment.